This is an experiment to measure the mass of a single electron. We shall take a small stream of electrons from a gun in a cathode ray tube, like a small television tube. We shall bend the path of the stream with a magnetic field and measure the shift of the spot where the stream hits the end of the tube. Here is the tube. This is the screen that glows when bombarded with electrons. Here is the gun with heated cathode and a large potential difference, about 800 volts, between gun cathode and gun muzzle that accelerates the electrons down the gun like this, so that they emerge with high speed V and kinetic energy a half mv squared, which we shall compute in a minute. I could bend the stream with an electric field. Inside the tube here, there are two plates like that, and I could apply a battery to them. On, off, on, off. But that wouldn't tell us anything new, because we've already used that tool, an electric field, to speed up the electrons in the gun. So I shall use a magnetic field. I might bring up a magnet like this. Close, away. In, away. But to get a magnetic field that I can compute, I must use the magnetic field due to a current in a wire. I shall run a long straight wire along above the tube, drop it down, bring it back under the tube, and make a magnetic field that way. I'll fetch my circuit. Connect to the battery. The rest of the circuit is arranged. Ammeter and switch. This long straight wire here isn't really a single wire. It's a bundle of 5 wires. So the current that the ammeter shows goes along here 5 times, down and round 5 times around the circuit. So I have 5 times the ammeter current going this way, making a magnetic field round and in like that. And 5 times the ammeter current going that way, making a magnetic field round and in like that. Both the magnetic fields run the same way, and having these 2 wires makes a more uniform field in the middle region. Look at the field with a compass. On. The field points that way across the direction of the electron stream. Now look at the electron stream when I turn the current on, off, on, off. Remember that when a stream of electrons, or any charged particles, is shot across a magnetic field like that, the stream is bent into the arc of a circle. We shall measure that circle in a moment. But first, let's see what information we can get from our measurements. This is a simplified picture of the apparatus. There is a bundle of 5 wires carrying current that way and back that way to make the magnetic field. The 2 essential measurements are the gun voltage V and the effect of the magnetic field. This potential difference, as you will see in a moment, will tell us the kinetic energy, half mv squared, of each electron as it comes out of the gun. The magnetic field B, due to the current in these wires, bends the stream from a horizontal straight stream like that into the arc of a circle so that the spot shifts from here to here. From the field and the shift, we can get the momentum, mv, of each electron. Then we know half mv squared and mv. And from these 2, we can separate out v, the speed of the electrons, and m, their mass. the mass of a single electron. I don't want you to think this is going to be an accurate measurement. There are too many difficulties. The magnetic field, for one thing, isn't uniform enough. I should be glad if our result is within 10% of the result of accurate measurements. In fact, this is what I should call an experiment of principle, to show you how good measurements could be made. Even if the final result is wrong by as much as 50%, I should still regard this as an important atomic measurement. Now let's make the actual measurements. First, the gun voltage. I shall read the voltmeter. The voltmeter reads 762 volts. Gun voltage V equals 762 volts. We know from our Millikan experiment that 1 volt is 1.60 times 10 to the minus 19 joules per elementary electric charge. Put that in. V is 762 times 1.60 times 10 to the minus 19 joules per elementary electric charge. This potential difference is the energy transfer in the gun from electrical form to kinetic energy for each elementary electric charge. So the kinetic energy of one electron emerging from the gun, half mv squared, is 762 times 1.60 times 10 to the minus 19 times one charge. It's that number of joules. Let's just work that out. It's about 1220 times 10 to the minus 19 joules. Remember that. We shall need it later. Now let's turn to the next measurement, the bending of the stream in the tube when the magnetic field is applied. The magnetic field pulls on the stream with a constant deflecting force. It doesn't speed up the stream, but only bends its path into a circle. The force provided by the magnetic field is B, the magnetic field, times Q, the charge, times V, the speed. And here, the charge is 1 elementary electric charge. The force needed for motion around a circle is, as you know, mv squared over the radius of the circle. This provides that. So B times 1 times V must equal mv squared over r. This is something we've had before. mv squared is twice the kinetic energy. We go back to our first calculation. Here was the kinetic energy, half mv squared. We want mv squared, which is double that, 2440 times 10 to the minus 19 joules. We'll put that in, and then we have B times V is equal to 2440 times 10 to the minus 19 over R. We want V, but we don't know B or R. We must measure B, and we must measure the radius of the circle, R. Now let's measure the radius of the stream. Travel distance down the tube from gun muzzle to screen, 29.0 centimeters. Now let's use a tape to measure the shift of the spot. We'll use a centimeter tape. Turn the current on, 6.4 centimeters. Let's just mark that on my meter stick, 6.4. Try it. We could calculate the radius by geometry, but I'm going to use a trick to make it simpler. I'm going to draw a life-size picture here. There's the gun, there's the stream going straight ahead. I shall mark the travel distance, 29 centimeters, to the screen there. And the distance, the spot, was shifted down 6.4 centimeters to there. What we want to know is the radius of a circular arc that starts out horizontally there and moves through that point. I shall find it by matching with the shadow of a disk. Dim the lights, please. That's too curved. Better. That's too shallow. It's right, somewhere just about there. Let's clamp it and then adjust it carefully. That's it. Now, there. We're ready to make the measurement. There's the center, which I'm marking with a circle. There. Here's the arc. Lights up, please. The radius is from there to here, 70 centimeters. 70 centimeters. Radius, 0.7 of a meter. R equals 0.70 meter. Now here, we can divide through by B and have V equals 2440 times 10 to the minus 19 over B times R, which is 0.70 of a meter. Now let's measure the magnetic field B. We'll read the ammeter and measure the coil. The current is 10 amps. The distance between the wires is just about 30 centimeters. 15 centimeters from this wire and from that wire to the middle region where the stream runs. 0.15 of a meter. Here's the record. Let's calculate B. The current runs along 5 wires that way, down and back along 5 wires. 5 wires, 10 amps. We want the magnetic field halfway between top wire and bottom wire, and that distance is 0.15 of a meter. From your text, you know that the magnetic field due to a current in a straight wire, B, is given by a constant times current over distance out from the wire, distance. Here, there are 2 bundles of wire, so we want twice that. So B is equal to 2. For our set of units, the constant has the value 5.12 times 10 to the minus 45. That arises from the choice of newtons for forces and elementary charges per second for currents, times the current. 5 times 10, that's amps, times 0.625 times 10 to the 19th to turn it into elementary charges per second, all over distance 0.15 of a meter. Now, I knew before we started that I was going to use 10 amps in this coil. So I calculated out the value of this field, and I know the answer. It is 2.13 times 10 to the minus 23. Let's put that into our main calculation. Here it is. B is 2.13 times 10 to the minus 23. Now we can calculate V. V equals 2440 times 10 to the minus 19 over B, 2.13 times 10 to the minus 23 times 0.70. Let's work that out roughly. 2 into 2440 is about 1200. Divide by 0.7 raises that to about 1600. 1600 times 10 to the minus 19 plus 23 plus 4. 1600 times 10 to the 4th. 16 times 10 to the 6th. 16 million meters a second. 16 million meters a second. In kilometers a second, 16,000. In miles per second, 10,000. That's the speed the electrons come out of the gun at. 10,000 miles per second. Now we can calculate m. We can put the value of v into the kinetic energy calculation we started with. mv squared, twice the kinetic energy, equals 2440 times 10 to the minus 19. V squared, we know, is 16 squared, actually it's a little more, times 10 to the 6th squared, 10 to the 12th. mv squared over v squared will give us m. I'm not going to finish the calculation. I'm going to leave you to work it out yourself. I think you'll find the result is within a few percent of the official value, 9 times 10 to the minus 31 kilogram. Before we finish, let's take one more look at the tube. There's only one spot. You know that all negative electrons have the same charge. The single spot shows that they all have the same mass. Atoms come with many masses, but all electrons are the same.